Welcome to the Peacademia course on basics of semiconductors. This lecture will cover the crystal structure. Let's start. By the time you finish this lesson, you will learn what a crystal is, crystalline, polycrystalline, and amorphous semiconductors, unit cell, and the silicon crystal structure. In the previous lecture, I introduced the energy band concept. The energy band is different from the energy diagram, and it is formed when atoms create bonds with each other. There are different types of bonding, including covalent and ionic. As far as we should be concerned in this course, we mainly deal with the covalent bond. In terms of the arrangement of atoms in a material, there are three types of structures. The first one is crystalline. In a crystal, atoms are arranged in a three-dimensional lattice, and the pattern of atom positions repeat. The lattice shape depends on the bonding between atoms to a great extent. For example, the lattice shape of silicon is diamond. The second structure is polycrystalline. The structure has multiple crystalline structures, each developed in different orientations. Each area in which a crystalline structure is developed in a specific orientation is called a grain. The third structure is amorphous. In this structure, atoms are randomly distributed in a solid. The crystalline structure is used when high-quality electronics properties are required. Since it is too difficult to grow a crystalline structure, it has the largest cost. RFICs are a good example of where the crystalline structure is used. The polycrystalline structure is used when the cost is more important than quality. The electronics performance degrades in a polycrystal because of defects created by the grain boundaries. The solar panel is an example of where the polycrystalline semiconductors are used. Electronics properties of amorphous structure are the poorest and are the cheapest at the same time. Thin film transistors in flat panel displays are normally made of amorphous structured semiconductors. While crystallography is an entire course for itself, in this lecture I try to introduce some of its basic concepts that could help us to better understand the following concepts we'll face in this course. In a crystal, we have lattice points. A lattice point can be anything. It can be an atom, a molecule, or something else. Each blue sphere in this two-dimensional lattice resembles an atom. Another concept to talk about is the unit cell. A unit cell is the simplest unit that is repeated to produce an entire crystal. If a unit cell contains only one atom, we call it a primitive unit cell. A primitive unit cell is sometimes called a simple unit cell, and it is not unique. We are interested in unique unit cells because by looking at the repeated patterns of unique unit cells, we can say if a semiconductor is crystal, polycrystal, or amorphous. For example, this square is a unique unit cell and its repeated pattern creates a crystal. Here we looked at a 2D structure, but what if I have a 3D structure? Auguste Brouet, a French physicist, thought about crystallography for long, and he showed that there are only 14 different ways of arranging lattice points in a three-dimensional space such that at any point the view is the same at any other point. There are 7 crystal families, and the one we care more about is the cube. In the cubic lattice family, there are 3 Brouet lattices. The first one is the primitive cube. At every edge of the primitive cube, there is an atom which is shared with 7 other primitive cubes. As a result, we can say that every edge of the primitive cube has half a quarter atom. Since this unit cell has 8 edges, the total number of atoms in this unit cell is 1. The second cubic lattice family is the body-centered cube. Everything in this unit cell is similar to the primitive cube except that there is one atom right in the center. The total number of atoms in this unit cell is 2 and can be calculated by this equation. The third cubic family lattice is the face-centered cube. This unit cell is similar to the primitive cubic unit cell, but with this difference that there is an atom on each face. The atoms on each face are shared with an adjacent face-centered cubic unit cell. Since a cubic unit cell has 6 faces, the total number of atoms in this unit cell is 4 and can be calculated by this equation. Often, we refer to each one of these unit cells by the Pearson symbol. The Pearson symbol for the primitive cube is Cp, for body-centered cube is Ci, and for the face-centered cube is Cf. Since silicon is the most used semiconductor in the industry, I think it's a good practice to take a closer look at the silicon crystal unit cell. Silicon is crystallized in a diamond structure. Diamond lattice structure can be thought of as 2 interpenetrating face-centered cubes with an offset of 1/4 of the body diagonal. It might be hard for you to imagine how the silicon diamond looks like by just looking at this image. Indeed, the imagination of the silicon diamond lattice was hard for me by just looking at a 2-dimensional figure. So to fully understand how a silicon diamond looks like, I made a wooden model for myself, just to better understand where atoms are placed in the silicon diamond. Creating this model took me a couple of days, but it was worth it. I just turned it around a couple of times so you can take a better look at the structure from different angles. You may ask why the study of the unit cell is important. Let's see what we can get out of this study. The silicon unit cell is cubic. The cube length at each direction is 5.43 angstrom. We call this length the lattice constant. The shortest interatomic distance between the silicon atoms in a unit cell is 1/4 of the body diagonal, and that is 2.35 angstrom. Let's count the total number of atoms in a silicon unit cell. The atoms on the edges of the silicon unit cell are shared with 7 other unit cells. So each edge has a coda of 1/2 of an atom. We have 8 edges. Each face has an atom which is shared with another unit cell. Therefore, each face has a coda of 1/2 an atom. We have 6 faces. Finally, there are 4 atoms inside the silicon unit cell. So in total, we have 8 atoms in a silicon unit cell. Another parameter to obtain through studying the unit cell is the density of atoms, or the number of atoms per volume. That is 8 divided by 5.43 angstrom cubed. The result is 5 times 10 to the power of 22 atoms per centimeter cube. We can also calculate the density of silicon. The atomic mass of silicon is around 28 AMU. 1 AMU equals almost 1.66 times 10 to the power of minus 27 kilogram. Density is the total mass divided by the volume of a unit cell, so the density of silicon is around 2.32 gram per centimeter cube. These numbers will be later used to calculate other parameters. In this lecture, I talked about the crystalline, polycrystalline, and amorphous structures, unit cells, and the silicon crystal structure. In the next lecture, I will cover the electrical properties of materials. Thanks for joining this lecture of Peacademia.